Hello, I'm Darren Underwood, Chief Technology Officer here at Interval Zero. Today I'm going to give you a high-level look into the RTX 64 scheduler. This is a primer for you to understand the basic workings of RTX 64. This information will help you develop software that will take advantage of RTX 64's unique native 64-bit SMP platform for real-time embedded systems. So let's get started. Okay, let's discuss the RTX 64 scheduler and its characteristics. So since RTX shares a platform with Windows, it's important to understand that the RTX 64 scheduler is independent and autonomous from the Windows scheduler. It's a clear distinction to really understand, as there are two schedulers on this platform, the Windows scheduler and the RTX scheduler. Like Windows, the RTX scheduler uses threads for its operation. With that, there are many threads. There's interrupt service threads, user threads, timer handlers, etc. From the scheduler's perspective, there is nothing special or unique about these types of threads, because at its basic form, the scheduler simply uses the execution state and the thread priority to determine which thread should be executed on a given processor. Now let's take a look at the characteristics of the RTX 64 scheduler. Basically speaking, the RTX 64 scheduler is a preemptive, priority-based SMP scheduler that is capable of doing round-robin scheduling. Now let's take a closer look at these in detail. So diving right in, first and foremost, RTX 64 is a thread priority-based scheduler. There are 128 levels of thread priority in RTX, 0 being the lowest priority and 127 being the highest priority. Now, thread priorities affect only the processor that they're on, and as such, priority cannot be used as a synchronization mechanism across multiple cores. And as I stated earlier, there are no special types of threads within RTX, and as such, there's no requirement for a thread reservation or a priority reservation mechanism. Now let's talk about the preemptive nature of the RTX scheduler. RTX is a fully preemptive scheduler, and by that we mean that threads are immediately switched at their current state of execution. Now what this means is that threads are not allowed to run to completion before an activated thread is switched in. Now there are types of events that cause preemption, and it's good to understand what those are. Some examples of those are, for instance, a higher priority thread is activated, which is obvious. A next may be that a object is being waited on by the thread, such as a wait for single object. The thread itself can also call a sleep function with a 0 parameter, which indicates to the scheduler that the thread is yielding the rest of its time on that particular processor. And finally, the time quantum timer expires. This is effectively the round-robin mechanism that we've talked about. Speaking of round-robin, in RTX 64, the time quantum mechanism is available, but it's not enabled by default. And the value of the time quantum timer is settable either through the control panel or programmatically through the management API or the real-time API. And it's very important to note that the time quantum only affects threads of the same priority on the same processor. With the previous characteristics in mind, we can now discuss what SMP means within RTX 64. I refer to it as SMP on your terms, for the simple fact that RTX does not do any automatic load balancing, which means that the developer is in full control of which processor a thread executes on and when. The developer must specify which processor a thread is to execute on. If he does not, the thread is simply executed on the base processor of the owning process. Now, once a thread has been executed on a given processor, it can be moved to other processors, along with APIs that give detailed information, timing information about the thread execution times. The developer can develop a load balancing scheme that is optimal for his application. Now, with those fundamentals in mind, let's move to the whiteboard and bring this all together. Now that we understand the scheduler and how it works, let's step through a few scenarios on the whiteboard. So the few structures I have drawn already up here is on the left we have a thread list, and this is the master list of threads that the scheduler has. Next to it, in these two blocks, these are going to be our processors for this scenario. We'll have processor 0 and processor 1. And above those processors, or logically on the processor, they each have what we term as a ready queue. Now what the ready queue is essentially the sorted list of threads that have been scheduled for that given processor. So let's start with a single thread. thread 1. And let's give it an arbitrary priority level of 10. Now we start thread 1 on processor 0 in this scenario. So thread 1 gets started on processor 0, which means that the processor's ready queue now has a listing for the first thread. And once that thread is activated, it runs essentially forever because it's the only thread on processor 0 at this time. If we start a second thread, thread 2, and we give it a higher priority value than thread 1, and start it on the same processor, in this case processor 0, then that will cause a preemption event, and that will then activate thread 2 on processor 0. So now thread 2 is the active thread on P0, and T1 is in a wait state. So let's move to the next processor and start a third thread. In this case, let's give it a low process level, or priority level, of 5 in this case. And let's start it on processor 1. Well, again, since thread 3 is the only thread running on processor 1, it will be active. And since it's running on its own processor, even though it has a lower priority level than threads 1 and 2 on processor 0, both processors are running their threads in parallel. If we start a fourth thread, in this case, let's start at the same priority level as thread 3 and on the same processor. Since they have the same priority level, each have priority level 5, and let's assume that we have thread quantum activated. In this case, the scheduler will ping pong between thread 3 and 4 being active, since they both have the same priority level, they're on the same processor, and the time quantum is set. So for instance, if the time quantum value was set to 5 milliseconds, every 5 milliseconds the scheduler would activate thread 3, and then the next 5 milliseconds thread 4, and continue back and forth in that condition. The next scenario I want to talk about is actually moving thread 1 from processor 0 to processor 1. In order to do that, we have to suspend thread 1. So if we suspend thread 1, that gives us the ability now to set its processor. So now we can set thread 1's processor value to P1. So now thread 1 is sitting here, but notice it hasn't yet activated because it's still in a suspended state. So thread 3 and 4 are still being ping-ponged back and forth. Now, let's resume thread 1. So as soon as thread 1 resumes, it causes a preemption event, which preempts then the execution of thread 3 and thread 4, and T1 now becomes the active thread on processor 1. So I hope this gives you a little insight into how threads and scheduling actually functions. You should now have a basic understanding of the RTX 64 scheduler and how it works. These are a sample list of functions from the real-time API that are used for thread management. Refer to the RTX 64 documentation for details on how to use these. Understanding the scheduler in RTX 64 is one of the best ways to develop effective software for this powerful platform. Thank you, and stay tuned for more technical training videos from Interval Zero.